Hello, welcome back. In this video, I want to analyze the magnetic force on a wire, which is going to follow, it's going to have a circular pattern, arc to it, with some radius, r, and it's going to be in the presence of a magnetic field, and we'll have the magnetic field going out of the board in this video. So I have little dots there, and it's supposed to be evenly spaced in red. Now, the formula for the magnetic force, we've already seen a couple times. So the force on this wire should be the current times the integral of ds vector cross the magnetic field. So that's the formula for it. Now, because the path of the current is on a circular, is tangent to a circle, ds is going to involve the tangent to a circle or unit vector, which would be the theta hat, the unit vector in the direction of increasing angle. And then we have to do calculus on it. So what I wanted to start with was by reviewing the polar unit vectors, and then once we have them, we can take cross product with them, and then also I will remind you of the relationship of the polar unit vectors to the Cartesian unit vectors. And when it comes time to actually do an integral, a lot of times that's the easiest form to use. So there's going to be a little bit of a review here. But don't forget where we're headed. We're going to come back to this kind of circular arc problem and apply the formulas in the end. All right, so let's kind of review this. So let's go back to the beginning. Okay, so let's draw out the x, y plane, and let's go and draw a circle of radius r. And let's pick a generic point on that circle. So if you were standing right here, and I ask you to take a step in the direction of increasing radius, you would walk diagonally out that way. And so the radial unit vector will be the vector that point in the direction of increasing radius. So at this angle, r hat is what we call that unit vector, would point over here. If, on the other hand, you were standing over here, then r hat would point that way. Okay? And it'd always be a unit vector, but the angle would change. And it's clear that r hat changes with the angle. It's not a constant unit vector. It depends upon where you're standing in the xy plane. It's not too hard to kind of see that r hat has to be positive in the x direction in the first quadrant and positive in the y direction in the first quadrant. It has to, when you're standing along the x-axis, it has to be straight to the right. You're standing at the y-axis, it has to be straight up, and it has to be periodic under shifting theta by 2 pi. So it's not too hard to guess that r hat equals cosine theta times x hat plus sine theta times y hat. When it comes time to do integrals, this is usually the version I like to use just because all of the angular dependence is explicit because the Cartesian unit vectors are constants. All right. Theta hat, on the other hand, is the unit vector in the direction of increasing angle. So if you're standing at one of these points, let me change colors here. So if I was standing right here, if you were to increase the angle, it would move along the blue arrow. So that must be theta hat, or the direction of theta hat. And similarly over here would be theta hat. So you see that theta hat is always perpendicular to r hat. That's just because r and theta are always independent. So moving in one is not at all moving in the other direction. The other thing we notice is that just as r hat depends upon theta, we expect theta hat to depend upon theta. So there, it's a little tricky. You have theta, the vector, or sorry, you have theta, the coordinate, and we have theta hat, the vector. And for those of you in dynamics, we also have theta vector, which points in the third direction. So don't get them confused. Keep it straight in your mind. So what I see is that when theta is 0, if you're standing along the x-axis, theta hat points in the y direction. And when you're standing along the y-axis, theta hat points in the negative x direction. So it's not too hard to guess that theta hat must be minus sine theta x hat plus cosine theta y hat. That, just try it out and you can see that it points, evaluate these two vectors at nice, 0 and 90-degree intervals or points along the circle. And you'll see that these are the right vectors. All right. Theta hat points along the circle, which means that the path up here in my example that I eventually want to come back to actually points in the negative theta hat direction because it's going clockwise, whereas mathematicians define positive angles to be counterclockwise. Okay, so that is one thing. We will come back to that. The other thing that's kind of nice to know, we will use this at different times too, is that if I go back to my my circle here, and I have r hat and I have theta hat. So this is x and this is y. Z is into your eye. So let me just, in fact, I don't need the circle. I apologize. What I really want, so here's x and y. We know that z is in the direction kind of out of the board. So here's going to be r hat. Here's going to be theta hat. And z hat is into your eye. Okay, because z hat would be in the direction of increasing z. Okay, so we know we're going to have to do all these cross products, and I know you guys are now experts, especially those of you who have been listening to me in dynamics, and you know that x hat cross y hat is z hat, and y hat cross z hat is x hat, and z hat cross x hat is y hat. But we haven't done too many in polar form. So let's just work it out. Z hat would be out into your head, into your eye. Z hat cross r hat is theta hat. So let's write that down. Z hat cross r hat is theta hat. Just picture it and work it out. R hat cross theta hat is z hat. And then it turns out theta hat cross z hat is r hat. Let's check that out. Theta hat cross z hat is r hat. And then if you reverse these are the positive ones. If I do r hat cross z hat is minus theta hat, and theta hat cross r hat is minus z hat, and z hat cross theta hat is minus r hat. Okay, so these are the cross products between, I suppose, cylindrical coordinates. You could do the same thing in spherical coordinates, but first you have to define the unit vectors, and that's where I was hoping to give you guys that technology with using Jacobians and metrics, but it just didn't happen. Okay. So make sure you know these. Let's do an example. All right, so the example I want to work out is the following one. We're going to have a wire, and it's gonna have this weird shape. I don't know. Everyone in the world does it, so we'll do it too. I don't know why it's so important. Length L, length L. We're going to say that this is on a half circle of radius R. We're going to say the current is going this way. So we have current I. And we're going to go ahead and say that the magnetic field is into your eye. And we're going to assume that the magnetic field is constant. Okay, so I have a constant uniform magnetic field, and I have a current carrying wire, which has this weird shape, which is a combination of two straight lines and an arc. We already worked out the straight line portions, so that's going to be a piece of cake. The real work is to evaluate the net force on this arc. And I'm going to go ahead and just kind of carefully work through the vector analysis. Okay. All right. So the net force, the total force, is going to be the force, 2 times the force on each of a wire, or a straight wire, plus the force on the arc. And it's a half circle. Well, this one's easy. The force on a straight wire, we already found that, and it was I, L vector cross B. And so let's work that out. I cross B, B's into your eye. The force is going to be straight down. So this will be I, L, B down. Okay. So that's what we get for that. And then we just have to double it for each segment. So that part's taken care of. Let's focus on the circular portion. The force on the arc, make sure you guys can see that, equals I times the integral ds vector cross B. Okay. And I can write ds as, so this is going to be the integral of r d theta. Now that's the magnitude of the arc length, so this better be a positive quantity as I integrate it. And then, which basically tells me I need to integrate from 0 to pi. Even though the current kind of starts at the angle of pi and flows to 0 as I'm following it. D theta is in the, I want the d theta to always be positive because it came from the magnitude of ds. So that's where that comes from. And then I need to multiply by the unit vector in the direction of the current. Well, that's going to be minus theta hat cross the magnetic field. Well, if I have x to the right and y is straight up, let's assume that's what I have, then z is into your eye. So the magnetic field is going to be B times z hat. So I have to work out that cross product. So the force on the arc is I. I'll go ahead and pull out the R. That was a constant. And I have an integral from 0 to pi d theta. And then I have to evaluate minus theta hat cross z hat. And I'll go ahead and pull out the constant magnetic field B. It is positive because I said the magnetic field was out of the board, which would be the positive z direction. Okay, well, and I could go ahead and pull this minus sign out front. That's easy enough. And I have to evaluate theta hat cross z hat. Well, let's see here. So theta hat goes clockwise cross z hat. Theta hat cross z hat is in the r hat direction. So this would be r hat. Okay, theta hat cross z hat is r hat. That was one of the positive ones that we found before. Okay, so now that's fine. And then now I have to do an integral. Remember, r hat is not constant. The polar unit vectors depend upon theta. So when you do this integral, you can't just pull it out. You have to remember that this is a function of theta. We wrote it down before. I'll write it down now. And we have to do that integral. So this becomes minus I times r times b times the integral d theta from 0 to pi of r hat. But that's nothing other than cosine theta x hat plus sine theta y hat. The integral of cosine is sine, but when I evaluate it at pi and 0, it's going to go away, so that doesn't matter. So that tells you the x component cancels. Does that make sense? Well, let's think about it. On each one of these, I almost used my left hand. Don't do that. I have a current. So like focus on this little segment right here. I'd have a current cross the magnetic field, and it would give a force. So the force right here is to the right. So if I were to add up all the little force vectors in blue, I'm going to get a force going here, a force going here, a force going here, a force going here, a force going here. And as we go around, you'll see that the x components cancel, but the y components add. So it makes sense that this one gives 0. In fact, we could have just said that it had to be, and could have just extracted the y component directly. But, you know, this is an excuse to do more math. So there you go. And then we have the integral of sine. Well, the integral of sine is minus cosine evaluated between pi and 0. So this gives me minus I r b times the integral, times minus cosine of pi plus cosine of 0 evaluated, or times y hat. But cosine of pi is -1, so this is double negative. It becomes 1 plus 1. This is just a 2. And so I get minus I times 2r times b y hat. So as indicated by the picture, the little force acts downwards, and it's equal to 2IRB, which is, again, just a famous result because everyone does the same example. I don't know why we always do this example, but we always do. All right, so then I'm pulling it back together. The total force was the sum of all of them, and the total force equals, well, I get a factor of 2, 1 from each L, and I get a factor of 2 from the circular arc. So this gives me 2I L plus R times B, and it points down in the negative y direction. And that's the formula for the total force acting on this bent wire shape. All right, so I guess that's the last force on a wire kind of problem I intended to do. Next up, I want to talk about torque on a wire, on a loop of wire, and that'll have applications to motors and generators and things like that. I guess mostly motors, but okay. So I'll see you next time.